Hello, everyone. We want to spend a little bit of time talking about confidence intervals. But before we get there, I want to review a little bit about sampling error because principles about sampling error are foundational to our understanding of confidence intervals. If you recall from previous videos, we talked about how a sample provides us with the best estimate of what a population parameter might be, but these samples are always incomplete windows into the population. Each time we sample, we're going to get a slightly different estimate just by random chance. And this variability among samples is what's referred to as sampling error. Now, as scientists, we usually collect only a single sample, and we need to draw our inferences from that single statistical sample. But statistical theory is based on the principles of what you would find if you were to collect many, many, many samples, if you were to repeat that thousands of times. So if we were to draw 1,000 random samples from a population, we might get a distribution of sample means that looks something like this, where most of the values fall in around 6, but sometimes just from random chance, we get an estimate of our sample mean greater than 10, and sometimes less than 2.5. And so this variability among samples is what's referred to as sampling error. Now, luckily, we can measure sampling error from the information contained within a single sample, and we don't have to repeat our sampling thousands of times. We can calculate what's called the standard error of the mean from the sample, which provides a measure of the precision of the sample or the amount of sampling error that we expect. And the standard error of the mean is calculated as the standard deviation of the sample divided by the square root of n. So what I want you to do is stop and think about this value for a minute. What would happen if we reduced the standard deviation in the sample down to 0? Or a very, very small number? The flip side is to consider what would happen if we made our sample size really, really, really large. What if the sample size was so large that it started to approach the actual population? Well, then we're sampling such a large proportion of the population that our sample mean is going to be very consistently close to the true population mean. As a result, the standard error of our mean will get very, very, very small. So in either of these cases where the standard deviation of our sample gets very small or the sample size gets very large, we have a situation where the sampling error gets greatly reduced and each of our successive samples is very consistent in their estimate of the mean. So we can use our standard error of the mean then as a measure of the precision of our estimate. So here we have a typical example where a scientist draws a single sample and tries to estimate a population parameter from that sample and only the information contained within that sample. So here we have a statistical sample of 100 genes from the human genome where the researcher has estimated the length of each of those 100 genes in units of nucleotides to try and draw some inferences about what the average length of genes in the human genome actually is. So in this case, the sample mean is equal to 3,328.1, and we have a sample standard deviation of 2521.6. We can then use this information on the standard deviation and the sample size to calculate the standard error of the mean as 252.16. And this provides us then with a measure of the precision of our estimate. So we can report our sample mean as 3,328 nucleotides plus or minus 252. So this standard error then gives us a sense of how much that sample mean is likely to vary from sample to sample. So now that we've reviewed sampling error, we can move on to talk about confidence intervals. Confidence intervals simply represent a range of values surrounding our sample estimate that is likely to contain the true population parameter. Whenever we talk about confidence intervals, we need to specify the level of confidence that we're talking about. Most often, 95% confidence But in some cases, we might report 99% confidence intervals or perhaps 90% confidence intervals. Confidence intervals are calculated directly from the sample data, and they extend above and below the sample mean. So they represent a range of values spanning that sample mean. The calculation of confidence intervals we're not going to get into right now, but the details are based on the underlying principles of sampling error. So things like the sample standard deviation and the sample size are both going to influence the width of our confidence intervals. So if we go back to our example of the average length of genes in terms of nucleotides in the human genome, we can calculate from that statistical sample what the lower and upper 95% confidence intervals are for those gene lengths. And so then we can state with 95% confidence that the true length of genes in the human genome falls somewhere between 2,828 and 3,828. So 2,828 represents our lower confidence limit, and 3,828 represents our upper confidence limit. So what does 95% confidence actually mean? This is a really challenging concept to understand, and this is where statisticians can get a little bit nitpicky about the words that we use to describe confidence. A 95% confidence interval means that 95% of the time when we calculate confidence intervals in this way, they will contain the true population mean. But it's not appropriate to say that there's a 95% chance that the true mean is within an individual confidence interval from a single sample. The reality is that either the true mean is within that interval or it's not. It doesn't occur or not occur with some chance or probability. And the reason for this is that we're talking about, in this case, only a single confidence interval that either includes the true population mean or it doesn't. We'll never really know. But the principle of confidence intervals is that if we were to collect a bunch of samples and calculate a bunch of confidence intervals, 95% of the time, those confidence intervals would capture the true population mean. So what I want to do next is to work through a really nice tutorial that Whitlock and Schluter have put together online associated with your textbook to walk through an example to help you get a better sense of what confidence intervals are all about. So I'm going to add this link to the website so that you can see it directly. And I've just clicked through to their website here to show you a bit of an example. So this is a population of fish that we're trying to collect a statistical sample from. And what you can do is to click on this Make a Sample button here. And what the program is going to do is select 10 fish from this population that has a true population mean length of 105 millimeters and a population standard deviation of 30 millimeters. So let's click on Make a Sample here. And what you can see is that the program randomly selects 10 fish from the population and creates a little histogram of the lengths of those fishes and reports the sample mean and the confidence intervals around that sample mean. Okay, so in this case, we have a sample mean of 106.6 and a lower confidence interval of 98.8 and an upper confidence interval of 114.3. Now, if you see at the top here, these are 95% confidence intervals. We can also click this button to change it to 99% confidence intervals. Okay, so what's nice about this tutorial is you can do this multiple times. Let's take a second sample. Okay, you can see that that mean is a little bit lower, 100.7. Let's do it again. And let's do it again. Now, you can see that because these are statistical samples and we're not measuring the entire population of fish, each time we collect a sample, we get a slightly different estimate of the mean length of fish. And this is, of course, due to our sampling error. So let's do this a few more times. And there's a nice button here that lets us do this a whole bunch of times. So we're just going to let it run through and run through. This is all just random. It's a simulation, so it's all done randomly. It's not, the books aren't cooked in any way here. And we're just going to let it run for a while. Okay, each time it's collecting a different sample of 10 fish from this population. Okay, and let's stop it here. Okay, so now we've collected 41 different statistical samples from this same population. And each of those 41 samples has its own sample mean and its own confidence intervals. And you can see that these differ as a result of sampling error. Okay? Now, whenever we collect a statistical sample, we don't know what the true population mean is. That's never known to us. That's what we're trying to infer using statistics. But in this case, in this simulation, we know what the true population mean is. We've set that with this bar over here. So the true population mean is 105 millimeters. Okay? Now, what our 95% confidence intervals mean is that 95% of the time, our confidence intervals are going to encompass the true population mean. Or conversely, 5% of the time, the true population mean is actually going to fall outside of our confidence intervals. So if you look at our simulation here, where we've performed or collected 41 different statistical samples, you can see that in 38 of those cases, the true population mean fell within the confidence intervals. But in 3 cases, the true population mean fell outside of the confidence intervals. So you can see that these are denoted here in red. Okay? And overall, the simulation has calculated that this represents a success rate, meaning the true population mean falls within the confidence intervals 93% of the time. Now, it's not exactly 95% of the time, but if we were to run this for a really long time, the simulation would converge on 95% success, because that's how confidence intervals are calculated, such that they capture the true population mean 95% of the time. But remember that scientists don't collect thousands and thousands of samples. They typically collect a single sample, and we need to draw our inferences from that single sample. Now you can see that if we were to be the scientists that collected this sample down here, we would have been correct in that our confidence intervals would have encompassed the true population mean. But 5% of the time, we're going to be completely wrong. And the true population mean is going to fall outside of our confidence interval. And we never really know when that's happened. We just are comfortable with the idea that 5% of the time, our confidence interval is not going to capture the true population mean. Now, if we're not comfortable with that, and we're only comfortable with the true population mean falling outside of the confidence interval 1% of the time, then we can switch to 99% confidence intervals. So I'd encourage you to take a look at this simulation. I think it'll really help you to understand sampling and confidence intervals, and I'll put a link to this on the statstree.org website. So we've talked a bit about how confidence intervals are based on the principle of sampling error, and that confidence intervals are smaller when sampling error is smaller. So what I'd like you to do at the end of this video is to then think about how changes in the sample standard deviation and the sample size will affect the width of our confidence intervals. So what I'd encourage you to do is to take some time exploring that tutorial to test some of your predictions based on the questions above. In the next video, we'll talk a little bit more about basic probability and how we might use this in our statistics.